Welcome to a complete PCB prototyping tutorial. Keep the items listed here ready before you start making the part. To make the PCBs, we will require Excellon/Gerber design files. Samples can be downloaded from the video description. We will then convert these files using a software called FlatCAM into G-code. This G-code will be loaded onto the machine control software called GSender, which you will see in the video as well. Once FlatCAM is open, we navigate to the folder containing your PCB design files. First operation, we will load the Gerber files. In this case, the top layer, the bottom layer, and the board outline. Similarly, the next step is to open the Excellon files. In this case, we have two Excellon files. Note that in the left panel, the 5 files that we have opened are visible. They are separately visible as Gerber and Excellon files. Here you can right-click and either enable or disable specific plots. You can also change the color of each of these plots so that they are easier to visualize. I'm setting the top layer to blue and the bottom layer to yellow. The drill holes are already in red. You can leave it like that in magenta or purple for the outline. The two types of drill holes here, NPTH, is the non-plated through holes, and PTH are the plated through holes. Since this is a two-sided PCB, we will open the two-sided PCB tool. This tool is used to generate the geometry for as we are trying to create a two-sided PCB board. In this example, we will have to create the features on the top side of the PCB, and then we have to turn the PCB board and finish the features on the bottom. So essentially, it requires us to flip this board after we're done with the operations on the top. And that is where this two-sided PCB tool is going to help us. So as we are going to flip the bottom layer, I choose the source object as the Gerber file for the bottom layer. We also need to provide a reference along which this board will be flipped or mirrored. So in this case, we have the option of choosing a point, like the origin or a specific point on the workspace, or we could choose a box, and that's what I'm going to do in this case on clicking the box. Option, we are asked to enter that reference object for the box, and in this case, we can easily take the Gerber file for the board outline as the box reference. Also note that it is possible to mirror this board or flip this board along the X or the Y axis. And in this example, we will choose the X axis along which the mirroring operation will happen. And once all of these options are selected, you can go ahead and click on the mirror button and watch the bottom design flip on the right side visualization panel once the bottom layer is mirrored. The next thing we need to do is create some alignment holes along which this board is going to be, which is going to assist us to flip this board accurately. And for that, you use the bottom options here for the PCB alignment. You can choose a drill bit here. I choose a 4mm drill bit, and you can choose points freely from here by using this add button. So you simply click on the add, and then you click on the workspace around the board, and you can add a couple of holes. Like so, after adding the points where you want your alignment holes to be drilled, you can generate the geometry for those holes, and you can see that the software has created your alignment holes. Now, in this case, on our example, the board outline is not a regular rectangle or a square. It has its own irregular shape. Therefore, since the cutout operation of the PCB from the bigger PCBB copperclad has to happen after the bottom operation, we also have to flip the board outline, and that's the operation I'm going to do next. All of the options remain the same as the previous mirror. It's just that the source object changes to the bottom outline or the board outline. Now, after the two-sided tool, we are back to the Project tab, and you can see that under the Excellon section, there is a new file called Alignment Drills, which is created as a result of the alignment holes that we created using the PCB tool. And also note that the board outline and the bottom layer, although they look unchanged here, but they have been mirrored using the PCB two-sided PCB tool. So next, we are going to generate the machine code or the CNC input or the G code for the top layer. All of these follow the same process. We start with a Gerber file. In this case, we generate a geometry for that Gerber file, and then we use the geometry to generate a CNC job object. So let's take a look with the first top layer. I'm going to disable every other plot so that it is not very cluttered and it is easier to see or visualize. So to start, simply double-click the Gerber file for the top layer. This will bring us to the Properties window where we see the properties of this Gerber object. What is important for us here is to choose the kind of tool. So we could do an isolation routing, an NCC routing, which would be to clear the non-copper areas, or we could also use the cutout tool. We're going to start with the isolation routing, which is going to create a file to isolate the tracks from the rest of the board. We also have some other options here like transformation to transform like scale and offset. I'm going to leave them unchanged here. On clicking the isolation tool, we are taken to the isolation tool window, and the things to note on this window are that that flat camera suggested by default that we use a 0.1 millimeter V bit. So if you see in the tools table, it's recommending that we use a 0.1 millimeter V bit. But then again, you can choose what kind of bit you want by simply clicking on this drop down. You can use a V bit or a circular bit or a ball end bit. And you also have the option of adding any tool from your tool library if you have set up one. In this case, I will go ahead with the 0.1 millimeter V bit. I leave the rest of the options as default. So I'm going to have just a single pass with an overlap of 10%. And once I'm happy with the options on this page, I click Generate Geometry. Once you click the Generate Geometry, a geometry object is created for you with the properties that you see on the screen. So it has held on to the previous tool selection, that is the 0.1 millimeter V bit. If you notice on the right-hand side on the visualization panel, you can see red lines where it has generated the geometry for the toolpath, which we will create next. The other options that you could specify here is the angle of the V bit. In this case, I leave it at 15 degrees. The Travel Z option is to set the height for the Z for rapid movement. Then you have the options for the feed rate. I'm setting both X and Y and Z to 300 millimeters per second. Then in case you have an automatic spindle, you can obviously set the spindle speed. But in this case, I have a manually controlled spindle, so it doesn't matter. So there is no tool change in this operation because we are using a single bit, so I can leave the tool change unchecked. In case you need a specific preprocessor, you can choose one from here, but the default is GRBL or GRBL, so I will leave it at default. We can leave the rest of the options with the default values, and next we can generate the CNC job object by clicking on this Generate CNC Job Object button. Upon clicking the Generate CNC Job button, we are taken to the next window, which is the CNC Job Object window. Notice in the right side visualization that we have the toolpath visualization, and it has also generated the CNC code, and we have to save this code now by clicking on the Save CNC code. I give it a convenient name in the order of the operations I would want to perform. So I call this file 1_top layer isolation. Now let's take a look at the CNC code that was created for us. You see this is an NC file. So it starts with some comments on containing all of the parameters that we defined, including the tool diameter, the feed rates, the rapids and heights and so on. And then you have a normal G code for the isolation routing. We can see that as a result of the previous operation, we have created the geometry of the isolation routing and also the CNC job. These files are now visible in your left panel. We can disable these plots also so that it is easier to visualize the remaining operation. So I'm going to disable them. Now the next operation that we're going to do is to create the geometry and the CNC job for the drill holes. And I'm going to start with the plated through holes. So we double click on the file. On double-clicking the file, we are on the next screen, which shows us the properties of that Excellon object. We can see here that there are a total of 156 holes on this PCB board, along with 3 slots. So we will have to do 2 separate operations, one for drilling the 156 holes and second operation for the 3 slots. Note that the holes have drill bits of varying sizes from 0.3 millimeters all the way to 1.4 millimeters. And this is where we are going to define how exactly we are going to drill these holes. So like I mentioned earlier, we will have to do the slotting operation in a separate second operation. So I will deselect the slots, 3 slots. Now coming to the parameters for these drill holes. The cut Z represents the depth at which you want these drilling holes the holes to be drilled. So I will use -2 millimeters. Multiple depths is an option you would want to use if you want to use spec drilling. But in this example, I'm just going to drill the entire 2 millimeters in one single shot. So I will uncheck that, then travel Z I keep at 5 millimeters. The feed rate at 300 and the dwell option is again optional if you have a automatically controlled spindle, in which case you can add some seconds for the spindle to ramp up to its full speed. But as in this option, in this example, we are using a manual control spindle, so it doesn't really matter. Moving on, if you come to the common parameters, one important option to check here is the tool change option. If you don't check the tool change option, then the operation will happen only for the first drill bit, that is for 0.3. So once we check the tool change, now the program generated will include all of the tools that we selected above. So note that the tool change height for Z needs to be at a sufficient height so that you have enough space to insert, remove an existing bit, and insert a new bit. So I am going to keep that as 80 millimeters. The end move Z represents the height at which the bit will be placed after the end of the job or when it pauses. And similarly, if you want a preferred X and Y end move, you can do that. And once these options are set, you can generate the CNC object. So on creating the CNC object, you are presented with this screen with the options that you've specified earlier. You can also see the visualization of the various tool paths generated for the individual drill bits. So if you're satisfied with all of this, you can go ahead and save that CNC code. Let's save this file and take a look at the file generated or the code generated. In the code, you can notice that it was generated for all of the tools that we selected or all of the bits and the different diameters, and you can see that it has specified the spindle speed and the feed rate, and so on. One interesting thing to notice here is that every time there's a tool change, you have a piece of code there to pause your operation where you would then, turn off the spindle and change the bit and then resume your operation. So now when you go back to your project tab, you'll see that the CNC job for the drill operation is present there. So we have to create next the code for the 3 slots. So in this OP, in this case, I will double-click on the Excel on File again, and this time I'm going to choose only number 7, which is the 3 slots in this case from the table, and I can give them or rather we can enter the properties of the slot itself. So the milling diameter in this case will be the diameter of your tool, which has to be either 1 millimeter or lesser than 1 millimeter. So I choose 1 millimeter, and then we can go to mill slots. So click on mill slots. You are presented with the geometry object for the mill. Just like before you can choose a bit, in this case I am going to use a circular bit of 1 millimeter, and again cut at a depth of -2 millimeters. Same parameters for the travel and the feed rate, and so on. There is no tool change in this case. We can go ahead and generate the CNC job and then save that job. So now that we've created the slot operation, you can see that the geometry and CNC job objects are present in the Project tab. You can also verify this on the right side visualization screen. So this will be followed by the drill operation for the non-plated through holes, which is exactly the same. So in this case, it is just a single operation with a 3 millimeter bit, and every other parameter remains the same, including the cut depth. We will not need a tool change here, obviously, because there's just one bit we can generate the CNC object for that. And so the non-plated through holes are done. The next operation will be to create the CNC job object for the alignment holes. The alignment holes were the holes that we created using the two-sided PCB tool earlier. This process is exactly same. We double-click on the Excellon object, look at its properties, then we click on the drilling tool. We are presented with the drilling tool page, in this case the cut. The Z depth will not be 2 millimeters, instead it will be, let's say 5 millimeters. In this case, based on the thickness of your wasteboard on which you placed your PCB. And the reason for this is because we need the alignment holes to be drilled into the wasteboard, and while flipping the PCB, we will use that hole along with some dowel pins to align our PCB. So we can go ahead and create the CNC job and save the file for the alignment drills. Now we are left with just 2 more operations. One is, after flipping the board, we'll have to do the isolation routing on the bottom of the board, followed by the cutout operation to cut the PCB out of the bigger PCB copper clad. So the isolation routing operation for the bottom will be exactly like we did for the top layer. So the steps repeat. We set the properties as seen in this image and also generate the geometry and the CNC code and save the CNC code. Now you've created the bottom layer. Now, finally, we can generate the CNC job object for the board outline. So I double-click on the Gerber file for the board outline. Please note that in this case, we are not going to use the isolation routing tool. Rather, we are going to use the cutout tool from the Gerber object panel. On clicking the cutout tool button, we are presented with the cutout PCB panel. And here there are a few options to specify. The first is the tool diameter, which in my case, I will use a 2mm bit. Then I want to cut it out at a depth of 2mm, and I can use multiple depths in this case. So it will take out 0.6mm at a time. Also, we have an option to specify tabs. So the tab size, I keep it at 0.5mm. As mentioned as the gap size here, there are 3 types of tabs. I use the default, which is bridge, and the number of tabs is 4. Finally, we can generate the geometry, and you see the geometry created on the right-hand side panel. You now have the geometry with the 4 gaps left on all 4 sides of the board, so these gaps will not be milled, and these 0.5mm tabs will be useful to hold the PCB board in place when the cutout operation is happening. And once the operation is complete, we can simply snap the board out of the larger plate. So I'll go ahead and create the CNC job. So one peculiarity here is that we are not presented with the Generate CNC Job option here. But if we go back to our project panel, we see that the geometry for the cutout is generated, and we can then double-click that file and go back to the panel where we have the Generate CNC object. Just like the other jobs, you can specify your CNC job parameters and generate the CNC job. We are now done with all of the operations on FlatCAM. I have generated 7 files, starting with the top layer, the drilling for the plated holes, slots non-plated holes, the alignment holes, then the bottom layer, and the cutout. I have not included any non-copper clearing operation here. But if that's something that you would want to do instead of the isolation, you can go ahead. It's quite the same in terms of options and parameters. We are not going to directly have the PCB copper clad mounted on the CNC machine. We always use a wasteboard. In this case, I am using a 6mm fiberglass sheet, and the way I am clamping this board is to first stick it onto our base plate using double-sided sticky tape. I then clamp them using steel clamps, and the reason I do this is because if we only clamp the surface on a board like this, it's possible that it bulges around the center. So in order to prevent the board from bulging and moving around, we stick it and then we clamp the board. Also notice that the operator's hand is quite hairy.
Typical clamp installation, you have a T-nut, washer, some kind of a bolt and nut, and then the standard clamps. So you put your T-nut into the rails. Have your washer on top. Put it into your clamp. These teeth sit into the lock into each other. It's installed. You can tighten this using a 8 spanner. Similarly, all 4 sides are clamped: 1, 2, 3, and 4. Now that we've installed the waste board and clamped it to the surface with the double-sided sticky tape for additional security, it's still not flat. This surface cannot be guaranteed to be flat because we are engraving PCBs with the tolerances of 20 and 30 microns. We need to first face this surface with respect to the spindle, and that is what I'm going to do next. I'm going to use a 10 mm flattened mill and mill this surface, onto which we can then mount our PCB copper clad board. So after running the facing once, you can clearly see that the waste board was not really level. It's evident from the fact that the bit engaged this part but not here. So I'm going to repeat the facing by lowering the Z0 by another 0.2, and hopefully we can get a nice clean square this time. After the facing operation, you see the baseboard is now flat with respect to the spindle. We can clean it up by lightly sanding with high grit sandpaper. I'm using 320. That should do. This will ensure that any burrs or fibers that are sticking out of this baseboard is also flattened, so that we have a perfectly flat surface. Next, we're going to secure the PCB copper clad to the baseboard. We're going to secure this using double-sided tape. There are many ways to clamp. This is just one of them. So I have 4 small strips of double-sided tape on the side outside of where we are going to engrave the PCB, and I have one small piece in the center so that it does not bend when the milling is happening on the other side. So the copper clad is now in place, and we are ready to start. So the spindle is loaded with the 0.1 nm V bit. I've positioned the uh, bit to the correct X and Y0, taking into consideration that we also have to put 4 alignment holes later. And while finding the Z0, you can get the bit probably 0.1 mm above the board to start off with, and then incrementally lower it through trial and error. I wouldn't advise trying to get the exact zero before starting the job itself. You might end up breaking the tip of the bit. You can lower the Z until there's enough place for a piece of paper to go in between the bit and the copper clad. Further adjustments we can try. So this paper is about 100 microns thick, so we can reduce in 50 micron increments until we get the bit to start engraving on the PCB surface. So the program is, the CNC job is loaded. We found the X, Y and Z0 in this case. starting of the drilling process, start with the smallest drill bit, in this case 0.3. The drill bit is loaded with the collar all the way up to the collet. This way, when we change the drill bit to the next one, we have to put the drill bit with the collar again all the way to the collet, so no need to find Z0 a second time. The program will pause at tool change time, and the spindle will stop at a sufficient tool change height. At this point, we can insert the next tool, which is 0.7.
So the program is, the CNC job is loaded. We found the X, Y, and Z0 in this case. slotting operation. The 1 mm end mill is loaded. I'm finding the Z0. Starting the operation. The slots are done. The next operation is the non-plated through holes with the 3 mm width. The next operation is the drilling of the alignment holes with a 4 mm bit. All operations on the top surfaces are done. That includes the isolation routing on top, the drilling of different holes using different drill bits, the slots, the through holes non-plated, and finally the alignment holes. Next, we can remove this board and flip it for doing the bottom layer.
Now that we're done with the top side, we have to flip it. So just like we did at the bottom, or rather when we were milling the top, we have to flip it and stick the PCB board to the waste board. And so I'm going to put 4 small strips of double-sided tape again and small bits in the center so that it doesn't bend. Then we can use the insert double pins into the alignment holes that we created earlier. And then slide the PCB board along those alignment holes, so that they are perfectly aligned and flipped. So take care that you flip it along the x-axis, because that's what we have defined, and also ensure that you're flipping the correct side. Now that we've flipped the board and stuck it back to the waste board, we can take out the double pins and we are ready to continue with our operation. So we can now start with the isolation routing for the bottom layer, followed by the final cutout.
end of isolation on the bottom layer.
This is where we start using the 2mm bit to do the cutout. Note the 5mm tabs which are left after the milling operation.
Cutout operation finished. 0.5 mm tabs. Post-processing required.
And now it's the turn for the plated through holes. The steps will be similar to what we have done before. Follow the instructor on the screen.